Look at the next one here. 7. A block of weight W is pulled along a horizontal surface at a constant speed v by force F, which acts at an angle theta with the horizontal as shown above. The normal force exerted on the block by the surface of the magnitude has a magnitude of what? Okay, so let's draw a free body diagram here, and let's try to identify all the different things acting here. So obviously we have weight, as always, pulling down. And that's equal to mg. We have a normal force from the surface pushing up. Label that Fn. And then we have this diagonal force being applied. Like this. Now we know this has an angle value of theta, and we'll just leave this as F, but what this is the applied force. And we could break this up into two parts, Fx and Fy. Fy is going to be found by doing F sine theta, because it's the opposite side. Fx is going to be found by doing F cosine theta, since it's the adjacent side. Now what we should realize here, since this box is not accelerating up or down at all, that the two forces pushing up on the box have to be equal to the force pulling down on the box. Once again, because it's not accelerating up, it's not accelerating down, so the net force in that direction must be 0, which means the forces acting on the box must be able to cancel out. So if the net force is equal to 0, and we know that's equal to the sum of the forces, so Fn plus F sine theta minus the weight, which is mg, we can find the normal force by taking the weight. I guess they labeled the weight here as W. Yeah, weight W. So we'll use that language instead. So we can find the normal force by subtracting, adding the weight and then subtracting force sine theta to both sides. Right? We want to get the normal force by itself, so the rest is just algebra. So if we do that, we get the normal force is equal to, once again, add weight to both sides, then subtract F sine theta, the weight minus F sine theta. So that would be answer choice B. Once again, most of this was just us realizing that the y component of this force had to add with the normal force, and that those two had to be equal to the weight. Once you realize that, rearranging that shouldn't have been that hard. I mean, you could have also started with the step like this. Hey, I know the weight must be equal to the normal force plus F sine theta. So subtract F sine theta from both sides. Normal force is equal to weight minus F sine theta. I mean, you could have done that too, instead of like, oh, well, the net force has to be 0, right? Either way works. Either way works. Alright, my heat just kicked in, so the sound quality might go down a little bit. Alright, so this one is tricky. Now, I'm going to basically say this is like a free question, because you have to understand here that the rope is not a rope, but the rope is an object. Now, what I mean by that is I've said multiple times in class that there can only be one tension force through like a rope or a string. And that's true when you consider the mass of the rope or string to basically be 0 compared to the other things in your system. But when the rope or string has a significant mass, it has to be treated as its own object. So the tension force throughout will not be equal. So it's kind of a trick question, okay? And I don't blame you for getting this wrong, okay? I'd expect almost everyone in the class to get this wrong. But it's a good opportunity to talk about a question like this if you do see it. I won't put this on the exam, okay? I promise that. I won't put this on the exam. But anyways, we have a uniform rope of 50 newtons. So what we have to think here is that we have two objects here. We have this rope object that has a weight of 50 newtons. And we have this box here, which is its own separate object, which also has its own weight downwards of 100 newtons. Okay. Now, what's going to be true here is that at the top of the rope, so if I'm looking from here, the top of this rope has to hold both the 50 and the 100 newtons. Okay, so the top of this rope, it's going to be 150 newtons. The bottom of the rope, it's only going to have to deal with this box. The bottom of the rope is only going to hold 100 newtons. Okay, because once again, in this example, the rope is its own, it is a separate object, right? Its mass is not zero. In all the other problems we've done, we haven't included the mass of the rope or the string at all. Because it's been so small, we basically consider it to be zero. And when that's true, the tension's all the same. But when it's not true, when the rope has its own mass, we have to consider it its own object. So the correct answer here is E. Once again, if you got that right, give yourself like 1,000,000 bonus points. If you got that wrong, don't worry about it. Don't worry about it. I didn't expect you to get that right. I just wanted to talk about it. Don't feel bad. Alright. Next set of questions here. Alright, number 9. When an object of weight W is suspended from the center of a mass... Hey, kitty cat. My cat is attacking my paper here. Please stop. When an object of weight W is suspended from the center of a mass of string as shown above, the tension at any point of the string is what? Okay. Well, let's think here. This object is not accelerating up or down at all. So the weight pulling down, okay, must be equal to the y component of these tensions pushing up. Right? Because we basically have two triangles here, two right triangles. Let's kind of draw this a little bit separately here. So we have these tension forces pulling up, and basically we have an angle here and here, and everything's basically equal about these two tension forces. So we could break them up into two parts, a y part and an x. Kitty cat, I swear. Paper is not a toy. Next part here. Okay. So what we have to understand here. Okay, kitty cat. He's being a jerk. What we have to understand here is that the weight, right, the force pulling down on these boxes is equal to both of the vertical components of these tension forces. Okay. Now let's think about how we'd get those tension forces, the y components of those. So let's remember that cosine of an angle is equal to the adjacent over the hypotenuse. In this example, the vertical is the adjacent, because it's the side touching the angle, that's not the hypotenuse. So if we're trying to solve for the hypotenuse, which is basically what we want, right? We want to know what the tension forces are. Then how we would do that is we'd multiply both sides by h and then divide both sides by cosine theta. So the hypotenuse would be equal to the adjacent side divided by cosine theta. Okay. Now we know here that the adjacent, this angle right here, or this side right here, I mean, okay, is equal to half the weight, right? Because both of these two added up. So I'll call this, so this is basically equal to the tension force, right? That's T, we'll call this Ty. Ty plus Ty equals W. Okay, and adjacent is basically Ty. Okay? So the two of these combined are equal to the tension force. I'm sorry, are equal to the weight. And the hypotenuse there would be equal to the tension force. So if W is equal to both of the y components added together, then Ty would basically be half of the weight. So the other way to find the tension force would be the weight divided by 2 divided by cosine of our angle. And that's basically the weight divided by 2 cosine theta. These guys. So once again, the important thing to understand here is that there's two of these vertical tension forces. One coming from this side, one coming from this side. The other important thing for us to realize is that cosine of our angle is equal to adjacent over hypotenuse. The adjacent was the same thing as the y component. The hypotenuse was the same thing as this overall tension. Okay. So once we realized that we could find the tension by doing the vertical tension force divided by cosine theta, and then once we realized that since these two add up to equal the weight, well then half the weight is equal to one of these, we realized that the tension force there would be the weight divided by 2 times cosine theta, simplifying this fraction here. Kind of a complex problem there. But the important thing was realizing two tension forces. Alright, number 10. So we have two objects. One is on a frictionless table, can move without friction on a horizontal table. The other one's hanging from a rope off of a pulley, frictionless pulley. So we could solve this in two ways. We could realize, well, once again, the acceleration of any system is equal to the outside forces acting on that system divided by the total mass. Well, the total forces acting on the system are basically just gravity, right? All the other forces here, the tension forces, are internal. And we should know by now that when we combine those equations, the tension cancels out. So it doesn't really get included in the net force. So if the net force is simply the mass times gravity, right, the weight, and I divide that by the total mass, which is 3m plus m of 4m, well, m divided by m cancels out. 1/4 of gravity. Okay. Now I could also solve this the other way, right? By writing a net force equation for each block based on its free body diagram. So let's do that too, just good practice. So for box M, we have two forces. We have the weight, which is equal to mg, and we have the tension force going up. Now the object is accelerating downwards, so the tension force is going to be smaller than the weight. For the other box, 3m box, we only have one force. We have the tension force, right? And that's equal to this tension force because this is a massless string. There's only one tension provided. Now, we can write net force equations for each of these boxes. Mass times acceleration is equal to the sum of the forces. There's only one force here, T. We do the same thing for this box. The mass times acceleration is equal to the sum of the forces. The weight causes it to move, so that comes first. Tension goes against that, so that comes second and is subtracted. Then I can combine these two equations. So when I do that, 3ma plus ma equals 4ma equals mg minus t plus t. The t's will cancel out. Rearrange to solve for a. Divide 4m by both sides. Then a. M's cancel out. G over 4. So either way works. Either way works. But it is 1/4 of gravity. Okay, notice guys, I'm using the same basic approach for all these problems. Free body diagrams, net force equations, go from there. Okay, it's all the same basic idea. Same basic idea. Next set of problems. Alright, incline. Plane 5 meters in length is inclined at an angle of 37 degrees as shown above. Block of weight 20 newtons is placed at the top of the plane and allowed to slide down. The mass of the block is most nearly... Well, this one, I think most of you guys got this right. This is pretty straightforward. Weight is your force of gravity. Force of gravity is mass times the acceleration due to gravity. Well, if the force of gravity is 20 newtons, I'm solving for m. I know g is 10 meters per second squared. Divide 10 by both sides. M is equal to 2 kilograms. So most of you guys did fine there. Figured that out pretty quick. Now, the next one says the magnitude of the normal force exerted on the block of the plane is most nearly what? Okay. So, we're not told anything about friction here. But we are told that the block is weighted 20 newtons, allowed to slide down, and that's basically it. Then we got a 3, 4, 5 triangle. Okay. So to find the normal force, well, all we have to understand here about the normal force is if we look at the free body diagram. Let's draw that. The block. Once again, we know that the weight is just going to pull straight down. I feel like I got to be consistent with my colors here, but I never am. That the weight is pulling straight down. Okay? And we know here, if this is 37 degrees, that the weight I can split up into two parts. I can split it up into a perpendicular component, FG perpendicular, and I can split it up into a parallel component, FG parallel. Now, the normal force, I know, goes perpendicular to the surface. And since this block is not accelerating up or down from the surface, right? It's not floating up in the air, it's not sinking down into the ramp. I should know that the normal force is equal to the perpendicular component of gravity. I should also understand that since this angle is also 37 degrees, that is equal to cosine times my hypotenuse, the weight. So FG cosine theta. And I know these values. The weight was given to me in the problem, so FG was already told to me to be 20 newtons. You guys can't see what I'm doing. 20 newtons times cosine of 37 degrees. And if I solve for that, I get about 16 newtons, roughly, after I round it. Once again, I don't need to know anything about how fast it's actually accelerating up or down this ramp at all. I just need to understand that the perpendicular part of gravity has to be equal to the normal force because it's not accelerating off the ramp or down into the ramp. I also have to realize that angle is equal to that angle. This is the adjacent side, and I can find that by taking my hypotenuse, 20 newtons, and multiplying it by cosine of my angle. My cat is crumpling up.